So I want you to pick up your phone, just, hold in your hand for a second.
Especially if you've just been, like, running a heavy app or something.
Right, exactly. If it's warm right now, you aren't just feeling a temporary battery drain or like a heavy processing load.
No, not at all.
You are literally feeling the laws of classical physics breaking down right against the limits of the atomic universe.
It's kind of terrifying when you put it like that.
But it's true. Every time you open a massive application or train a local AI model and that device gets burning hot against your palm, you are witnessing the absolute physical limit of the technology that built the modern world.
Yeah, we really are.
And so today, we have a deep dive specifically designed for you. We are going to explore what happens when the very foundation of our digital era simply cannot get any smaller. And more importantly, what bizarre exotic materials we are actually going to build tomorrow out of.
It really is a profound transition period. I mean, for the better part of a century, the digital age has coasted on one highly specific, incredibly reliable foundation.
Which is silicon.
Right, silicon. And we are currently watching that foundation just crack under the weight of our own computational demands.
So our guide for mapping out these cracks today is a piece from SpiralSeekr. It was published on April 14, 2026, and it's titled Beyond Silicon, Finding the Next Building Block of the Digital Age.
It's a great read. Really lays out the roadmap.
Yeah, it does. So our mission for this deep dive is to look past the end of the silicon era and, uncover the incredible atom-thick materials stepping up to save the future of our technology. Okay, let's unpack the physical limits of modern computing.
Let's do it.
Because before we look at the solutions, we really need to clearly establish the microscopic problem we are actually trying to solve here. We have to look at the king.
Yeah, undisputed king, which is silicon, like you said. And to understand why we are abandoning it, you kind of have to appreciate why we used it in the first place.
Right, why did it rule for so long?
Because it's practical. I mean, silicon has dictated the pace of technological growth for decades, primarily because it is essentially just highly refined sand.
Literally just sand.
Exactly.
Yeah.
It is extraordinarily cheap, universally abundant, and critically, it acts as a remarkably stable semiconductor.
And just to clarify for everyone, I mean, most people know semiconductors can act as both a conductor and an insulator, right?
Yeah, they do both. But the really critical part is how reliably silicon lets us control that state.
We apply a voltage, and boom, it allows electricity to flow. We remove it, and the flow stops.
That's the magic. That controlled flow is a transistor, the microscopic switch that gives us our ones and zeros.
And for, 50 years? The strategy for making computers faster and more powerful was simply just make the silicon switches smaller.
Yep, Moore's law. It dictated that we could double the number of transistors on a chip roughly every 2 years.
Just keep shrinking them down.
Right. We shrank them from the size of a fingernail down to the size of a red blood cell and then, down to the size of a virus.
Yeah. It's wild to think about that scale.
It is. But the SpiralSeekr text highlights the fundamental reality we've hit today. You just cannot shrink a physical object forever.
You hit a wall.
A very hard wall. We are now manufacturing transistors at a scale of just a few nanometers. We are talking about boundaries that are literally only a handful of atoms wide.
Right. And when you shrink a physical boundary down to the atomic level, classical physics just kind of takes a back seat, right? Yeah. And the bizarre universe of quantum mechanics takes the wheel.
That is exactly what happens. It gets weird.
The piece points to a really specific phenomenon that's causing the current heat death of our devices, quantum tunneling.
Yeah, that is the microscopic roadblock. So in classical physics, an electron is a particle, right?
Okay.
If you build a solid physical barrier, even a thin silicon barrier, the electron cannot pass through it when the switch is turned off. It is like throwing a tennis ball against a brick wall. The ball just bounces back.
Makes sense.
But at the quantum level, an electron doesn't act like a solid tennis ball. It acts as a wave of probability.
A wave of probability.
Right. It doesn't have a single definitive location. It just has a statistical likelihood of existing in a certain space.
So wait, if I'm visualizing this probability wave as we make the silicon barrier thinner and thinner, to pack more transistors onto a chip, the barrier actually becomes narrower than the electron's probability wave itself.
You're exactly right. The wave actually overlaps the physical wall.
That's crazy. So it's no longer like a bucket leaking water through a hole. It's more like trying to carry water in a bucket made of a chain-link fence. The water just flips right through boundaries where it shouldn't be able to.
That's a great analogy, yeah.
Or like a magician, The electron hits the wall, the universe rolls a quantum pair of dice, and suddenly the electron simply exists on the other side of the barrier. It bypasses the wall entirely.
That captures the sheer weirdness of the physics perfectly. The electron simply appears on the other side. The barrier hasn't physically broken, but the electron has tunneled right through it.
Which sounds like a massive problem for a computer chip.
It's a huge problem. In the microscopic circuitry of a high-end processor, those tunneling electrons represent raw, uncontrolled electrical current leaking out of the intended pathways.
Which explains the heat in my palm.
Precisely. When electrical energy flows where it isn't supposed to, it scatters and generates heat. It drains your battery without doing any useful computational work.
So it's basically just wasting power and cooking my phone.
Exactly. And critically, this is why processor clock speeds, like the raw gigahertz numbers, they largely stalled out years ago.
Oh, that makes sense.
Yeah, we literally cannot push silicon chips any harder or make the barriers any thinner without the quantum leakage generating so much heat that the chip literally melts itself. We have just run out of physical space.
But wait, if heat and quantum leakage are, like, the immediate existential enemies of our technology right now, why is this a two-part conversation?
What do you mean?
Like, why isn't there just one magical material we are hunting for to replace silicon across the board? Because right now, while we are searching for a new microscopic brain for our computers, we are simultaneously dealing with a massive surge in the need for heavy-duty, raw electrical power, right?
Oh, absolutely.
I mean, electric grids, superchargers, electric vehicles. How are we managing that brawn if silicon is failing us?
That's a really good question. The distinction between power management and logic processing is crucial here. The text highlights that we are already deploying real-world solutions for the power problem.
So the power problem is separate from the brain problem.
Completely. And you are right to separate them because routing heavy electricity and performing microscopic calculations are entirely different engineering challenges.
Okay, the article actually brings up a fantastic everyday example of this power solution that you might have plugged into your wall right now.
The fast chargers, right?
Yeah. If you've purchased a fast charger for your laptop recently, it's probably tiny. 10 years ago, laptop chargers were massive, heavy bricks that got incredibly hot.
Oh, yeah, they were awful.
But the new ones are the size of the standard phone charger, yet they push massive wattage safely. How are they doing that?
What's fascinating here is the material inside those modern power bricks. It isn't silicon.
Really?
Nope. It is a material called gallium nitride, or GaN, alongside its close cousin, Silicon Carbide, or SpiralSeekr. These represent a fundamental upgrade to how we channel serious voltage.
So GaN and SpiralSeekr.
Right. And the reason they succeed where silicon fails comes down to a concept called a band gap.
Okay, let's define that, because band gaps seem to be the secret sauce of this entire transition. What is a band gap?
Think of a band gap as the physical energy hurdle an electron has to clear in order to flow and create a current.
Like a literal hurdle on a track.
Exactly. Silicon has a relatively narrow band gap. A low hurdle, that's great for low-power microchips, but when you hit silicon with high-voltage, massive electrical pressure, the electrons easily spill over the hurdle.
They just jump right over it.
Right. The silicon loses its grip, the current leaks, and it generates massive heat. That's why those old chargers needed giant heat sinks and thick plastic casing.
So what makes gallium nitride different?
Gallium nitride is what we call a wide bandgap semiconductor.
Meaning the hurdle is much, much higher.
You got it.
So the atomic bonds in GaN hold onto their electrons with a much tighter grip. So even when you blast it with the heavy electrical pressure of a fast charger, the electrons don't just spill over.
And because they don't spill over, there is virtually no wasted energy.
Wow.
And no wasted energy means no heat. And no heat means you don't need all that bulky, heavy cooling equipment anymore.
That's why the charger is so small.
Exactly. You can pack the same high-voltage power delivery into a footprint a fraction of the size. That wide bandgap efficiency is exactly why gallium nitride and silicon carbide are quietly taking over the global power infrastructure.
So it's not just laptop chargers.
Oh, not at all. When an electric vehicle needs to dump massive amounts of energy from its battery to its drivetrain instantly, GaN handles the load effortlessly.
Which is incredible for the power grid.
Yeah.
But it brings me back to the core mystery here. I got to push back on this.
Go for it.
If gallium nitride is so incredibly efficient, so heat resistant, and holds its electrons so tightly, Why not just carve it into tiny microscopic switches and make it the brain of my smartphone?
It seems logical, right?
Yeah, why are we still looking for another material? Just slap GaN into everything.
I wish we could, but because the very thing that makes gallium nitride great at handling high voltage makes it incredibly difficult to use for ultra-dense microscopic logic gates.
Oh, because the hurdle is too high.
Exactly. To do logic processing, the billions of calculations a second required to run an operating system or an AI, you need materials that can switch on and off effortlessly millions of times a second using almost zero power.
Right.
GaN's high hurdle requires way too much energy to toggle at that microscopic scale. It is the perfect superhighway for raw power, but it is too heavy duty to act as the delicate, intricate brain.
Okay, that makes perfect sense. GaN solves the heavy-duty power grid problem. It is the brawn.
Yeah.
But the brain problem, the quantum tunneling, the melting silicon logic boards, that remains totally unsolved by GaN.
It does. We need something else.
So we have to pivot back to the atomic scale. Where do we look for a processor replacement, if not another rocky compound like silicon or GaN?
For the logic switches, we have to look toward a material that is universally abundant, but structural in a completely different way. The answer actually seems to lie in the foundational element of biology itself, carbon.
Here's where it gets really interesting, because we aren't talking about carbon in the form of a diamond or like a lump of coal. The source text introduces the Graphene Dream.
Yes, graphene. It is an engineering marvel that fundamentally changes how we think about physical structure. It belongs to a family of what we call 2D materials.
2D materials, like two-dimensional.
Exactly. And when we say 2D, we aren't speaking metaphorically. Graphene is a sheet of carbon atoms arranged in a repeating hexagonal lattice, a honeycomb pattern that is literally only one single atom thick.
The physical reality of that is staggering. A sheet of material essentially without depth.
It's incredible.
And the SpiralSeekr piece notes that if you take that flat honeycomb sheet of carbon and roll it up into microscopic seamless cylinders, you get carbon nanotubes.
Right, and carbon nanotubes possess electrical properties that almost defy common sense.
Oh, so?
Well, in traditional copper or silicon wires, electrons bounce around as they move. They crash into atoms, they scatter, and every single collision creates friction.
And friction means heat.
Right. That friction is electrical resistance, which generates heat. But in a pristine carbon nanotube, electrons experience something called ballistic conduction.
Ballistic, meaning they fire straight through, like a billiard ball gliding perfectly across a completely frictionless table.
Yes, exactly. They don't scatter.
That's wild.
There are almost no collisions at all. The electrons just glide through the carbon lattice with virtually zero resistance.
Or no heat.
Virtually none. Because they conduct electricity effortlessly, and because the tubes themselves are impossibly thin, just a few nanometers across, you can theoretically pack billions of them into incredibly tiny spaces without generating the massive thermal wall that plagues silicon.
Wow.
Carbon nanotubes solve the logic bottleneck beautifully on paper.
On paper is doing a lot of heavy lifting in that sentence, though.
It really is.
Because whenever a material sounds this flawless, frictionless, atom-thick, zero heat, there's a catch. The universe doesn't give us free lunches.
No, it certainly does not.
So what is the hurdle keeping a carbon nanotube chip out of my laptop today? Why don't I have one right now?
The hurdle is the absolute nightmare of manufacturing at the atomic scale.
Really? It's that hard?
It's brutal. The text emphasizes that understanding the physics of a single carbon nanotube is easy. Mass-producing billions of them perfectly is one of the hardest engineering challenges in human history. We don't carve them out of a block like we do with silicon. We have to grow them.
Growing them through chemical vapor deposition, right?
Yes.
Injecting carbon-rich gases into a blistering hot furnace over a metallic catalyst and just hoping the carbon atoms assemble themselves into these perfect little tubes.
That is the process. And the problem is, when they grow, you don't just get one type of tube.
What do you mean?
Depending on the exact angle the honeycomb rolls up into something called its chirality, the tube will either act as a semiconductor, which is what we want for a switch,
Okay.
or it will act as a pure metal wire. And in a furnace, they grow as a tangled, messy mixture of both.
Oh, man. And if you accidentally wire a microscopic processor with a metallic tube instead of a semiconductor, the switch can never turn off, right?
Exactly.
The circuit just shorts out. So you have to somehow sort them chemically after they grow, separate the pure metal ones from the semiconductors, and then, align billions of these invisible microscopic cylinders perfectly parallel to one another on a wafer.
That's exactly what you have to do. The manufacturing bottleneck is just staggering. The theoretical potential of carbon nanotubes is limitless, but our physical ability to manipulate them consistently at mass, commercial scales, is still, catching up to the physics.
But looking at the source text, even if we assume some brilliant engineer solves the manufacturing tomorrow and perfectly aligns a billion carbon nanotubes, I spot a massive theoretical flaw with graphene itself.
Oh, what's that?
We established earlier that computing is entirely about control. A transistor must conduct electricity to say 1, but it must also stop the electricity to say 0. If graphene allows for ballistic conduction, frictionless, effortless flow of electrons, doesn't it just act like an open fire hydrant?
You've zeroed in on the exact technical dilemma that kept physicists awake at night for years. Graphene is an unbelievable conductor, but as a pure single sheet, it entirely lacks a band gap.
Wait, it has no energy hurdle at all?
None. Zero. Without a band gap, there is no hurdle to stop the electrons. Graphene wants to conduct electricity constantly.
And if you cannot stop the flow of electricity, you don't have a switch.
No, you just have a really fantastic wire. And wires cannot perform logic operations. They can't run software.
So we need the microscopic thinness of a 2D material so we don't run out of space. But we desperately need the band gap hurdle of a semiconductor so we can actually turn the switch off.
Exactly.
How do we get the off switch back without reverting to bulky, heat-generating 3D silicon?
This is where the SpiralSeekr piece introduces an incredibly promising alternative. It's an absolute mouthful of a material, Molybdenum Disulfide, or thankfully MS2 for short.
MOS2. Let's dig into the physics of this one. Why does MOS2 fix the fire hydrant problem of graphene?
MOS2 belongs to a class of materials called transition metal dichalcogenides.
Say that 3 times fast.
I know it sounds incredibly complex, but structurally it is just a microscopic sandwich.
A sandwich.
Yeah. You have a single layer of molybdenum atoms squeezed between 2 layers of sulfur atoms. Like graphene, it is a true 2D material. The entire sandwich is still just a few atoms thick, sharing that incredible space-saving property.
Okay, so it's super thin.
Right. But the crucial distinction highlighted in the text is its electronic nature. Because of the way the molybdenum and sulfur interact, MOS2 naturally possesses a band gap.
It has a built-in energy hurdle.
It does. It can effortlessly transition between conducting an electrical current and entirely blocking it, even at the scale of a single atomic layer.
Wow.
It gives engineers the definitive off switch they rely on with silicon, but with the unbelievable thinness of graphene.
So what does this all mean? If we actually succeed in swapping out rigid chunks of silicon for atom-thick sheets of MOS2, how does that translate to the real world?
It's revolutionary.
Like, how does that change the physical gadgets you and I are going to buy in 10 years? Because I assume the end goal isn't just a smartphone that's, a millimeter thinner.
Oh, no. The implications go far beyond the thickness of a glass screen. When you transition from a 3D crystalline structure like silicon to a 2D sheet like MOS2, you gain something completely unprecedented in high-performance electronics.
What's that?
Sheer mechanical flexibility.
Flexibility.
Yeah. Silicon is a crystal. If you bend it, it snaps. It requires a rigid board and a protective metal case. But the text points out that atom-thick sheets of MOS2 are incredibly pliable. We are paving the way for high-powered logic processors that don't need to live inside a rigid box.
Wait, are we talking about genuine wearable tech? Not like a smartwatch with a heavy metal chassis strapped to your wrist, but processors woven directly into the synthetic fabric of your jacket.
Exactly. The technology could seamlessly conform to the shape of the human body. Because the transistors are literally atom-thick and can flex with the weave of a material, your clothing itself becomes the computational platform.
That is wild.
The physical form factor of our devices is going to radically decentralize.
The journey we've charted out here is staggering when you step back and look at it. I mean, for half a century, the entire modern era, every spreadsheet, every satellite launch, every generative AI model has been dictated by refining rocks and sand into silicon.
Yep, and it served us brilliantly.
It really did. But we hit the thermal wall. The components became so microscopic that the laws of quantum mechanics took over, and electrons began tunneling through barriers, leaking heat, and killing performance.
And our roadmap out of that dead end splits into 2 highly specialized paths.
Right.
For raw heavy-duty electrical power, the brawn managing our electric grids and vehicles, the future belongs to the wide band gaps of gallium nitride and silicon carbide.
And for the microscopic logic, switches the brain. We're entering the era of 2D materials. We have the frictionless dream of carbon nanotubes, provided we can solve the chemical sorting and alignment nightmare.
Big if, but yes.
And we have MOIUS 2, providing that critical natural band gap, allowing us to build atom-thick, flexible computers that fold right into our daily lives.
You know, if we connect this to the bigger picture, there is a profound, almost philosophical implication hidden deep inside this transition away from silicon.
Like what?
Think about the periodic table. If we successfully transition our logic architecture to carbon-based structures like graphene and carbon nanotubes, our technology will literally share the exact same fundamental building blocks as biological life.
Carbon is the anchor of all known biology.
Exactly.
Human beings, the dogs sleeping on the floor, the trees in the park, every organic cell is a carbon-based structure.
And for the entirety of human history, there has been a stark elemental divide between what is organic and what is artificial. Life is carbon and water. Machines are metal and silicon.
That's a huge divide.
But if the advanced AI models of tomorrow are running on processors built from carbon lattices, the substrate of our machines and the substrate of our bodies will be built from the exact same atoms, just merely arranged in slightly different geometric patterns.
That is wow.
This raises an important question. Where do we eventually draw the line between artificial hardware and organic life? When the foundation is exactly the same, the boundary between advanced technology and biology becomes remarkably blurry.
Which leaves us with one final, really fascinating concept to mull over. And it builds directly on that blurring of lines you just mentioned.
Yeah.
Think back to that burning hot phone draining its battery in your hand at the start of our deep dive. Right now, when a rigid silicon device breaks, we take it to a repair shop.
Right, you get the screen replaced or whatever.
A technician unscrews the chassis, pulls out a logic board, and hits it with a soldering iron. It is distinctly a mechanic fixing a broken machine.
Very mechanical.
But if the gadgets of tomorrow are essentially built out of the same pliable carbon-based material as living tissue, woven into our clothes, conforming to our skin, acting almost organically.
Where are you going with this?
Will we eventually stop repairing our broken machines with tools? Will we instead have to start healing them, using chemical processes the way a doctor treats a biological organism?
Oh, wow.
If our tech becomes carbon, the future of IT support might look a lot less like engineering and a lot more like medicine. Something to think about the next time your phone gets a little too warm.